Okay, so 16.9 is all about the acid-base properties of salt solutions. And we've actually seen this a little bit before when we were doing solubility last chapter in Unit 7, when we were looking at how an ionic compound can be more soluble or less soluble in an acid or base solution because one of those ions reacts with the H plus or the OH minus in water. And we're going to see sort of similar things going on here. But we're talking about starting with just an ionic compound. So not an acid or base, but starting with an ionic compound and then seeing how usually its conjugate acid or its conjugate base reacts with water. So here we can see, F minus. So this could be from an ionic compound like sodium fluoride, potassium fluoride, iron 2 fluoride. Any ionic compound that happens to have fluoride as its anion, as its negative ion. Well, since we know that that is the conjugate base of a weak acid, that it can react with water and actually pull a hydrogen off of the water, leaving behind OH minus. So if it is the conjugate base of a weak acid, it can actually turn the solution basic. So if you were to take sodium fluoride and put it in water, we would notice that the pH would be a little bit higher than 7. Here's another example, the aluminum ion. So if we did like aluminum chloride, for example, just some, regular old ionic compound, aluminum nitrate. When I put that in water, the aluminum ion will react with water. It is positive, so it will attract, right, that negative part of water, the OH minus, leaving behind H plus. That would mean that the pH was a little acidic. So this is called hydrolysis. And if you think of what that word means, right, it's lysis means breaking. So hydrolysis literally means like breaking up water. And so these particular ions have a property where they will react with water and pull off a piece of the water and therefore make the solution either more acidic or more basic. So similarly to what we did before, once we look at the ionic compound and we break it up into its anion and cation and think about, will the anion or the cation react with water? And it's basically, how do you figure that out? Well, would it form a weak acid or strong acid? Would it form a weak base or a strong base? So let's start with the negative ions, anions. Anions of strong acids are neutral. So that's, your Cl minus, I minus, Br minus, nitrate, sulfate, chlorate, and perchlorate, right? They won't react with water, so they won't be able to pull a hydrogen off of water, so no OH will be formed. But if it is an anion of a weak acid, right, they are conjugate bases. They will grab a hydrogen off of water, leave behind OH minus. This is also a great example of where we get those papas, right? The protonated anions of polyprotic acids. If I think of, CO3 negative, that can either gain an H or it could lose an H, right? So it could go either way. And what we would have to look at like the actual numbers, the Ka or the Kb. So cations, group 1 or group 2, metal cations are neutral. So these are the ones that are associated with strong bases, right? Lithium ion, if it was going to, it's positive. So it was going to pull an OH off of water. It would leave behind hydrogen, but it doesn't because lithium hydroxide is a strong base. So therefore, basically the other metal cations that aren't associated with a strong base would actually be able to pull a hydroxide off of water and make the solution acidic. That's what this particular question is talking about. Polyatomic cations are typically the conjugate acids of weak bases. We really talk about very few polyatomic cations in baby chem. The only one we talk about is ammonium, right? NH4 plus. And there's lots of ones that you look at, you're like, that's a weird ion. I haven't seen that before. And then you go, oh, I can kind of see how that's an amine that has a hydrogen ion with it. So this shows you some interesting things. This is the acid dissociation constant, so the Ka's of these transition metals. Remember, how the heck does a transition metal make an acid solution? Well, something like Fe2+, when it reacts with water, it's positive. What does it do? It pulls off the hydroxide ion off of the water. Maybe it makes FeOH2 and leaves behind 2 positive hydrogen ions. That's how it can have a Ka. You can see they're not all that big. And so these are sort of the 4 categories of, if I have an ionic compound, could it make the solution acidic, basic, or neutral? And what I always look at is just, can it react with water? And when it reacts with water, what does it do? Knowing that positive ions, right, are generally going to, we have to see, can they pull a hydroxide off of water? Negative ions, could they pull a hydrogen off of water? And then there's a few, different categories, like the ammonium example, and the ones where it could act as an acid or a base, in which case you would have to look at their actual Kas. So here are some examples. Let's look at these. So determine whether these solutions would make an acidic, basic, or neutral solution. These are just ionic compounds. Like, these could have been on the test last year in baby chem, just giving you the formula and you give me the name. So the first one is barium acetate. So I think about, well, what will be the 2 ions that it will form? It'll form a barium 2+ ion and the acetate ion. And then I look at the positive guy. Could he take the hydroxide off of water? Well, barium hydroxide is a strong base. So barium is not going to react with anything. But the acetate ion could pull a hydrogen off of water, right? Acetate is negative. What's the positive part of water? That hydrogen ion. It could make or let's write it like this, CH3COOH, and leaving behind OH minus, right? So what would be the pH of this solution? It would be basic. It would be greater than 7. The next example here, ammonium chloride. So break it up into its 2 ions, right? Does NH4+, could that react with water? And then you say, yeah, actually, it could react with water. It is one of the, we kind of know, it's the conjugate acid of the most common weak base, the ammonia. So yes, it's going to donate a hydrogen to water. It's going to make H3O+ and ammonia, NH3. So that is an acidic solution. And of course, will Cl- react with anything? No, it's not going to react with the positive ion of water, because if it did, it would make HCl, which is a strong acid, which we know strong acids don't form. Okay, and the next example, CH3NH3Br. So break that up into the ions. It must be CH3NH3+ and Br negative. And immediately I recognize the bromide ion. It can't grab a hydrogen off of water, therefore, because it's a strong, HBr is a strong acid. So Br negative isn't going to influence this. And then I think of the CH3NH3+, right? When I see that NH, I think of this could be like an amine. And in fact, yeah, this is the conjugate acid of the weak base CH3NH2. So when it reacts with water, it donates its hydrogen to water, making H3O+ and CH3NH2. So this again will be acidic. The next one, KNO3. What are the ions? K+, NO3 negative. K+, it's positive. Will it grab an hydroxide off of water? No, because that would be a strong base. NO3 negative, will it grab a hydrogen off of water? No, because that would be a strong acid. So this guy would be neutral. And then the last example here, we have aluminum 3+ and perchlorate negative. Perchlorate, that could grab if that grabs a hydrogen off of water, it makes that strong acid. So that won't happen. And then this is the positive ion. What could it do? Well, it could grab the hydroxide off of water to make aluminum hydroxide and leave behind 3H+. So this guy would also be acidic.